Hello, my name is Spencer Carboni from St. Bonaventure University. Today, let's talk about a method to predict agricultural pesticide liquid chromatography retention times via ab initio calculations. Thank you for tuning into my talk. We begin this study with a problem. Pesticides enable feeding of a vast number of people, but they come with their own challenges. Pesticides are typically large, organic molecules that leach through soil and impact groundwater quality and safety long after serving their intended purpose on crops. The organic structure of some pesticides enables biomagnification of the molecules up trophic levels. Studying pesticides requires costly reagents and equipment. Access to knowledge is thus restricted from this cost. So we wonder, how do we study pesticides without costly and dangerous reagents? Is there a theoretical framework to fall back upon to investigate pesticide properties? My inspiration to pursue this research project began when my university's research lab purchased a new liquid chromatograph. I had been planning an investigation on local produce pesticide load and retention in living systems. While seeking chemical standards to compare fruit samples with, cost and availability of reagents was largely prohibitive. Concentrated pesticide samples tend to have dangerous properties unsuitable for undergraduate university research. I found that published libraries of pesticide retention times are incomplete as structural development of these molecules evolves rapidly and internationally. Fortunately, ab initio analysis does not require costly reagents or exposure to any dangerous agents that could harm the student. An answer to our questions is to investigate pesticides through quantum chemistry density functional theory, or DFT for short. By developing a theoretical model by which to study pesticide molecular behavior in an analytic system, the liquid chromatography column, we can learn about the system with lessened concerns of chemical risk or monetary cost. Disseminating understanding of this theoretical framework will enable scientists to apply this technique to other classes of chemicals. The project enables identification and study of poorly characterized pesticide analogs and metabolites. Preliminary research came across an invaluable data source to this project on solid phase extraction. Research illuminated the quetchers, or quick, easy, cheap, effective, rugged, and safe technique for edible sample processing. This reference study is a residue analysis of pesticides found in grape samples, yielding many parameters including retention time and liquid chromatography column. These published and standardized retention times with large n equals 150 pesticides can be used to build regressions using quantum chemistry theoretical parameters. The model, if a tight fit, would predict behavior of pesticides in the liquid chromatography column without needing a reference standard. We see here 10 out of the 150 pesticides with their assessed retention times and other parameters. Of note are these retention times highlighted in green. In establishing this research project, my team and I developed many goals to operationalize the process. First, we employed quantum chemical analysis software, including Avogadro, TurboMol, and Cosmo RS, to generate optimized geometries for pesticide structures. Then, these optimized structures were used to generate theoretical chemical and thermodynamic properties. The generated properties were then compared to reference standards. Calculated properties were assessed against published retention time values in order to build regressions. Exogenous molecule properties were then calculated using quantum chemical software, and these properties were inserted into the regression, predicting theoretical retention time within the liquid chromatography column. In the future, retention time in the liquid chromatography column of exogenous molecules will be measured and compared to the theoretical retention time. The general workflow of this project included converting molecule names into 2D structures, which were then built in Avogadro software into 3D, roughly optimized structures. These were then imported into TurboMol and run on a Linux server cluster to produce optimized geometries, which were then exported into Cosmotherm, where various chemical and thermodynamic properties were calculated. Over the course of this project, many properties were calculated, including vibrational frequency and isotropic polarizability and anisotropy in TurboMol, log P over log D partitioning, flash point, boiling point, and density in COSMO-RS, and finally molecular weight directly from Avogadro. The basic mechanics of this research employ density functional theory, or DFT. DFT is a quantum mechanical model by which molecular properties can be predicted off of their ground state electron densities rather than by their wave functions. This technique combats the many-body problem by approximating the exchange correlation energy using density functionals directly. This employs functionals, so different DFT functionals approximate the exchange correlation energy differently. And as you see here, we have a diagram that shows the general approach of this in a graphical format. When applying density functional theory to explain behavior of a system, we need to choose a basis set that best explains the electronic behavior. So you may ask, which basis set? A basis set is a set of functions representing the electronic wave function in density functional theory. There are many choices available. The basis sets approximate the partial differential equations of density functional theory into computer processable algebraic equations. If you see a D at the end of the name of a basis set, this refers to the addition of diffuse functions. Diffuse functions are shallow Gaussian basis functions that reflect behavior of the tails of atomic orbitals distant from the nucleus. These improve representation of the anions or of transient negative charges, as may occur on oxygen atoms or in large intermolecular systems. The basis set used in this experiment was DEF2-TZVPD. The rationale behind this was that DEF2 enables a fast initial geometry optimization, while TZVP represents the valence triple zeta set and incorporates more ability to calculate polarizability. This set also includes effective core potential, or ECP, of rubidium or heavier atoms. This corresponds to the Popel set 6-311G from at 2DF and P, and this is the highest correlation to reference standards within the Cosmotherm X presets, which we see here are between TZVP, SVP, DMOL3, and our choice of TZVPD-fine. A software suite called COSMO-RS is the tool used to generate the theoretical parameters for this research. COSMO-RS stands for Conductor-like Screening Model for Real Solvents. It employs this mathematical calculation of mu, which is the chemical potential. This chemical potential can be used to calculate many other properties, such as melting point, flash point, boiling point, evaporation, solubility, osmotic pressure, partitioning coefficient, liquid-liquid extraction, chromatography, and even equilibrium chemistry. The software suite converts density functional theory's ground state electron densities into approachable values, such as normal boiling point or partitioning coefficients. The research in this study was conducted in Cosmotherm X, version 19.0.4, in a Windows platform. Cosmotherm X is the software tool used to operationalize COSMO-RS mathematics. As you can see, the software tool supports batch loading of your molecules, choice of your basis set, and even calculation of your favorite chemical properties. My advisor, Dr. Scott Simpson, has published in this area before, and much of the procedural knowledge for this paper was gained from this study titled Identification of Polybrominated Diphenyl Ether Metabolites based on calculated boiling points from COSMO-RS, experimental retention times, and mass spectral fragmentation patterns. This is foundational research for this present study that analyzes new emerging compounds of concern. It shows ways by which we can analyze potentially dangerous metabolites through ab initio analysis. After data for this research has been acquired, we will proceed onto the statistical analysis and regression construction. Equations have been generated in Microsoft Excel for correlation between each chemical and thermodynamic property and the molecule's published retention time. Construction of many multivariable regressions between all possible permutations of data will be included. This is achieved using an R code script with the highest R squared values indicating the tightest regression fits within the dataset. The percent error will be calculated between retention times calculated from all generated equations and published values. The smallest percent error regressions will show the tightest fits. All of the regression equations will be calculated in the absence of 5 randomly selected molecules, which will be reinserted into the generated model to assess the best fit between the theoretical value and the reference value for each generated multivariate regression. The future directions for this research are to apply the knowledge gained. We will be adapting this technique to explain the behavior of other chemical systems via ab initio technique. There is a focus on bioaccumulative, toxic, and persistent chemicals in our environment with this research. We want to publish the knowledge gained to assist research teams in developing their own predictive regressions. We will be assessing samples of produce using the Quetcher's technique, and we will run the isolate through our liquid chromatograph. We would like to develop a procedure to identify and quantify pesticide residual load on food samples local to us. We will develop an online database of our multivariate regressions so that anyone can find theoretical retention time of their compound of interest. We will be educating future researchers on this technology and this technique for research. I have been very fortunate through this research to have the opportunity to educate others via YouTube tutorials. My goal is to reduce the barrier of entry for density functional theory research. I want to improve access to chemistry fundamental and procedural knowledge and guide future researchers through the experimental procedures used here. Here is a screenshot of one of my procedural clips. Please check it out. I would like to thank you very much for your interest in our project and for tuning into my talk. If you have any comments or questions about our research or our findings, please visit the research team website linked below or contact us individually. I would like to thank my advisor, Dr. Scott Simpson, for your continued support and guidance through this entire project, and for my associate, Jonathan Antle, for his help with the statistics in this project. I would also like to offer a deep thanks to the ACS and to the National Science Foundation for your support of our project and of our research goals.